My name is Mason Whatley, and this is my material selection presentation for Asphalt. Today I'll be presenting research on polymer modified bitumen, optimization and selection, a study published in Materials and Design. And this paper explores how we can optimize asphalt performance by modifying bitumen with different polymer additives such as SBS, PW, and CR, and how we can use experimental design and selection tools to choose the best formulation for a given application. Now, the main challenge the authors address is something civil and pavement engineers deal with all the time, which is how do we design bitumen blends that perform well across a range of conditions without relying on trial and error or just picking from a manufacturer's catalog. Instead, they propose a more systematic approach, one that's both predictive and visual, by combining statistical modeling and material selection charts. So the scope for this research is to optimize different PMB blends to enhance its mechanical performance. And the key question is, how do cost-effective blends meet specific performance targets in terms of penetration and softening point temperatures? So the methodology in the study utilizes an experimental mixture design model by preparing a series of blends with varying the amounts of three polymer modifiers with a base 80 to 100 penetration grade bitumen. Then they used an augmented simplex lattice design and made 10 distinct MC and binary blends. Now the key properties measured were penetration, softening point, and penetration index, which altogether indicate the mechanical hardness, thermal susceptibility, and overall performance of the material. And the penetration performance index was calculated using a standard equation that relates the softening point and penetration values, which helped classify the thermal behavior of the bitumen blends. And additionally, the rheological performance was modeled using the equation for a complex shear modulus. So the first key result examines how different blends influence the softening point. So figure 2 on the left shows the measured softening point values for each blend. And the big takeaway here is that PW and SBS both dramatically improve thermal resistance, while CR plays a more passive role. So figure 7 on the right provides a helpful way to visualize this. And as you move up and to the left, you see materials becoming more stiffer and more temperature resistant. The MC blends, which combine all three polymers, occupy the most desirable top left corner of the chart. They outperform the binary blends by achieving better stiffness and thermal performance without necessarily increasing cost. So what's great about this figure is that it includes penetration index guidelines, so you can actually quickly assess where a material falls in terms of expected pavement performance. Now on to the second key result, which looks at how these blends impact penetration values and costs. Figure 3 on the left shows that PW is again the most effective at reducing penetration down to as low as 14 decimillimeter in one MC blend. SBS also helps, but CR has a much smaller effect. The reason this matters is that lower penetration generally indicates a stiffer, more rut-resistant binder, but stiffer doesn't always mean better if it costs too much. So figure 9 becomes really important here. It plots penetration index versus cost per ton. This is where the practical trade-offs become clear. SBS modified blends can reach PI values around +6, but they can also cost up to $1,300 per ton, while PW achieves similar PI values at lower cost. But what's really interesting here is the behavior of MC blends, as they can hit PI values up to +7 while keeping costs around the 900 mark, which is significantly more efficient than any single polymer formulation. So to wrap it up, the paper concludes that MC blends provide the best balance between performance and cost. SBS and PW are highly effective modifiers, improving softening point and reducing penetration. CR, although is weaker in performance, it can add value from a sustainability and cost perspective. The use of the Ashby charts and predictive equations makes it easy to visualize and select the optimal blend for a given application. And personally, I think this research is very well structured and practical. It especially is useful for pavement and civil engineers who want to make smart materials decisions without going through the endless trial mixes. The experimental framework is clear, the data is well analyzed, and my only critique is that more long-term or field data would really strengthen the conclusions, but as a design to manufacture tool, this paper delivers a lot of value.